In this lecture, we're going to be discussing how to determine effective 3D orthotropic material properties of laminates. Some of the figures were taken from the Engineering Mechanics of Composite Materials book, second edition, Isaac Daniel. Why is a good idea? What motivates the idea of finding effective engineering material properties? So say, for example, we have a situation where we have the top face sheet is of interest, um, but we're not as interested as the bottom lamina. So what you could do is you could represent the top face sheet with great detail, but in the areas away from the region of interest, at the bottom could be modeled as a row of elements that will be using effective engineering constants. So, in other words, effective engineering properties can be used to simplify a finite element model, is one way this could be used. Take another example. So we want to predict failure of a very thick laminate with a wrinkle in the outer plies of a composite pressure vessel, as an example. Since the wrinkle is in the outer plies, you can model this area ply by ply. So every lamina is represented as a single row of elements. And then the very bottom, um, say the bottom 60 plies, could be represented with a single row of elements, fairly coarse, but that one is going to have an effective uh, material properties representing all these plies that are put together. So this approach can increase the efficiency of finite element modeling by a significant factor. Another reason why effective engineering material properties can be of great use is for engineering design. Instead of testing every single combination of stacking sequences, we could determine effective engineering properties using analytical methods that will allow us to determine Young modulus, Poisson ratio, and shear modulus in a way that's efficient and without having to test. That does not preclude the need of testing. Testing should be done regardless, but this methodology to be presented today is a very good methodology that can be used for the analysis of composite structures and also for early preliminary design. So what are we trying to achieve? What we're trying to achieve is, given the 1, 2, 3 coordinate system of each ply, um, with the material principal directions, and X, Y, Z are the laminate directions that we will consider. But every ply will have a coordinate system 1, 2, and 3. 1 is aligned along the fiber. 3 and Z are aligned through the thickness. Um, and X, Y, and Z are the laminate coordinate system. What we would like to do is specify the material properties for a single lamina. As you can see here, E11 represents the modulus in the one direction. E22 represents the modulus transverse to the fibers. E33 represents the modulus through the thickness, through the thickness direction. Nu12 represents the Poisson ratio due to loading in the one direction, contraction in the second direction. That's what this measures, Nu12. Nu13 is loading in the fiber direction and measuring the strain in the third direction, that contraction in the third direction. Nu23 is another Poisson ratio that needs to be specified, and also the shear modulus, G12, G13, and G23. So we have 9 material constants that need to be specified for a lamina. And we need to specify it for each of these plies. So what we want to do, is, can I come up with laminate engineering constants for their whole stack put together? Can I come up with a EXX, EYY, EZZ that describes the modulus in the X direction, the modulus in the Y direction, and the modulus through the thickness direction? That is the goal that we're trying to achieve. So given the material properties at the ply level, can I come up with an effective material set of constants that describes the overall behavior of a laminate model? And here I have to specify, I had to somehow come up with these 9 constants. There could be more, as it will be discussed later. To achieve that, the first step is really to understand how we can transform a single ply whose lamina orientation may not be aligned with the laminate XYZ directions. So somehow we need to transform this so that we can come up with a material behavior in the X, Y, and Z for a single lamina. And then we can figure out how to do it for multiple lamina. So recall that the constitutive law that relates stress to strain is related through the stiffness matrix. And the stiffness matrix, the constants that go along with this stiffness matrix are determined from empirical data or testing. And so what we want to do is, these are defined in the lamina coordinate system. We would like to define C in an arbitrary coordinate system. That is what we're trying to achieve. Now note that we have used contracted notation to simplify the formula that stress relates to strain through this constitutive law. As you can see here, sigma 1, 1, sigma 2, 2, sigma 3, 3 are the stresses that act on a single cube, which act to expand the cube in 3 directions. Sigma 2, 3, sigma 1, 3, and sigma 1, 2 are shear stresses, which act to distort the tube. And as you can see here, this is the contracted notation that we're going to use to simplify how the stress and strain relationships are written. Recall that for orthotropic materials, we can derive the stiffness matrix that relates stress to strain using this relationship, which involves the 9 constants which can be determined through material testing. And note that these were defined in the principal directions 1, 2, 3 for single lamina. So in other words, if I know E11, E22, E33, Nu12, Nu13, Nu23, and G12, G13, and G23 in the lamina coordinate systems, where 1, 2, and 3 are defined as such, where 1 is aligned with the fiber, then this constitutive relationship shown here applies. Now, what we want to do, though, is we want to somehow transform the constitutive law that's aligned with the principal material orientations to the laminate system. So then we can later somehow come up with an approach to getting the effective laminate stack properties. I want to make a little slight modification to the equations that we have here. I will multiply by 2 in the diagonal terms, and then I'll divide by 2 in the strain vector, as you can see here. You still get the same result, but we're doing that to be able to apply a couple of tricks. And this will enable us to do some coordinate transformations that will allow us to convert this constitutive matrix from the 1, 2, 3 coordinate system, which is aligned with the material principal directions, to the XYZ arbitrary global coordinate system. That is the goal that we want to achieve. So let's discuss then how to come up with effective engineering constants for one lamina. As you may recall, we want to define the direction cosines as a matrix A, and A will be made up of these direction cosines. And this gives us the angle between cosine and the y-axis and the x-axis, cosine of the y-axis and the y-axis, cosine of the angle between the 1 and the z-axis, and so forth. So if we define these terms as m1, m2, m3, n1, n2, n3, p1, p2, and p3, we can try to figure out a way of relating stress in the 1, 2, 3 direction to the stress in the x, y, and z directions. So note that the direction cosines for single lamina is well known. Why is that? If I go here to the image that we had shown earlier, the one principal orientation along the fiber direction, the angle between that and the x-axis is known. The 3 and z-axis are aligned, so that will never change. But as long as the one axis rotates, the two axes will rotate too, because the 1 and 2 are 90 degrees apart. As a consequence, there's only one angle that varies. As a consequence, finding the direction cosines for every single lamina, it is very straightforward to do. In our situation, the angle between the cosine of 1 and z is 90 degrees. We can see that in this image. This is the one direction, this is z direction. The angle between 1 and z is 90 degrees, and the cosine of 90 is 0 degrees. We also have to find the cosine between the 3 and z orientations. And we can see here that these z and 3 are aligned, so the angle between them is 0. And as a consequence, the cosine between 3 and z, that angle there is 0, so cosine of 0 is 1. What you will find is that these two terms will be 0, these two terms will be 0, and this will be 1. And then these four terms here will be either cosine alpha or sine alpha, where alpha represents the pi angle. But regardless, in the most general formulation, we can call this M1, M2, M3 for the purposes of simplifying what we plan to do next. I invite you to take a minute right now, pause the video, and what you want to do is use this relationship and transform the stresses in this manner. So expand this equation using these terms for the cosines and substitute it here to demonstrate that the stress in the 1, 2, 3 lamina system can be related through this formula to the XYZ laminate system. And I'll take a second for you to pause the video. So congratulations if you pause the video and you figure out how to go about this. What you want to acknowledge here first is how many equations do we have here? We really have 9 equations. 6 are independent because the stress is symmetric. And so for the first term, I have sigma 1, 1, as you can see there. And now then I'll have AM1, AN1. And since M and N are repeated, summation is put in front of these A's, and M runs in 1 through 3, and N1 runs 1 through 3. When you expand this, you'll be able to find that these terms turn out to be M1 squared, N1 squared, P1 squared, 2N1, PN1, 2M1, PN1, 2N1, M1, and so forth. And so I invite you to derive these equations one by one to gain confidence that this transformation of stresses is going to work. Secondly, I want to point out that this formula that we're showing here is can be derived using the Morse circle. But here we're using a more general transformation formula that can be used very successfully. So again, through this formula, I'm able to transform from the laminar coordinate system to the laminate coordinate system and relate the stresses in this system to the stresses in the laminate system by this transformation relationship that we see here, that's 6x6. And again, I invite you to take some time to go through that and derive it. We can also, in a very similar fashion, transform the strain. We know the strains in the lamina system, and then we want to transform them in the laminate system, to the laminate system, using these transformation matrices. And this transformation matrix in a very similar manner. And once again, I invite you to go through the derivation of this. All you have to do is expand this formula, and you're going to have 9 components, 6 of them independent because the strain relationships are symmetric, the shear stress, epsilon 1, 3 equals epsilon 3, 1. And then what you want to do is expand this and use these representations to demonstrate that this column vector in the lamina system can be related to this column vector in the laminate system. And what you will find is this transformation matrix that relate the two. Again, why we're doing this is because I want to find a way of transforming the lamina coordinate system to the laminate coordinate system. So how do I determine CXYZ in the arbitrary XYZ system? So this is really what I want to do. I want to find a relationship that relates stress to strain through a constitutive law that's defined in the XYZ system. Recall that what we're trying to do in this image is that given the properties E1, E2, E3, and so forth, the material properties for the lamina system, what we want to do is relate that to the laminate system, X, Y, and Z. And so what I want to really do is find the constitutive law, but in this system. That is the end goal. And so that's what we're trying to drive towards. And to achieve that, the first step was relate stress in the lamina system to the laminate system. The next step was to relate the strain in the lamina system to the laminate system. And then finally, what I want to do is figure out a way of relating stress in the laminate system to the strain in the laminate system, because that has to be the constitutive law in the laminate system, which is really what I want to find. So what I can do, I can expand it as follows. I can expand the left-hand side as follows. As you recall, the stress in the lamina system is equal to this transformation matrix T. I'm going to call it T, to the laminate system. So if I want to isolate this, I have to find the inverse of T and put it on the other side. So I have T inverse times this column vector. I'm going to do the same thing later with the strain, but for now, this is equal to T inverse times this column vector. We also notice that this column vector is equal to C times the strain vector, and that was shown here. Stress equals to C times the strain vector in the lamina coordinate system, in the 1, 2, 3 coordinate system. And so now I have that. Now this strain vector is equal to T times this strain vector in the laminate coordinate system. How do I know that? We just derived that here. The strain vector equals the transformation matrix times the strain in the laminate system. That's exactly what I have done. This is equal to T times this column vector. And so when I compare this to this, and I compare this to this, what I realized is that this CXYZ, this constitutive relationship in the laminate coordinate system is really equal to this transformation matrices inverse of that times C, which is in the laminar coordinate system, times T, the transformation matrix. So all I have to do is do this huge multiplication. These are 6 by 6, these are 6 by 6, and these are 6 by 6. And I can calculate this term here to be able to find what CXYZ is for a laminate coordinate system. So given C in the laminar coordinate system, I can figure out a way of finding CXYZ, the constitutive law, but now in the laminate coordinate system, XYZ. So this is where we have landed. So stress equals the T inverse times C times T, and then the strain vector in the laminate coordinate system, where T was given by this expression, and I ask you to derive that to see if you can achieve that. C is given by this expression here, and so all you have to do then is to find CXYZ, which you should be able to find fairly readily. And these extra 2's came about because we added those since we made the strain vector without those 2's, okay? And that came out earlier in time. So to get the transformed engineering constants. So for example, say that I have E11, E22, Nu12, G12 measured for lamina, but I would like to know the engineering properties in the laminate principal directions, EX, EY, Nu-XY, GXY. So what does that require? That requires us to transform the engineering constants, but it will be much easier to do the whole procedure starting with the compliance matrix S, which we will add we'll multiply by 2 again for purposes of transformation. So if you have recalled earlier, I can relate strain to stress using this compliance matrix. And the beauty about this compliance matrix is that you don't have to memorize it because you can derive these formulas using the principle of superposition, as we had discussed earlier. But it's easier to work through this because here I will find CXYZ, fine, but how do I relate that to the engineering constants? So instead, let's work in this system. So strain in the laminate system equals XYZ times stress in the laminate system. Strain in the laminate system equals the T inverse times the vector in the lamina system. But this is S, the compliance matrix in the laminar coordinate system times the stress in the lamina system. And this lamina system stress can be related to the stress in the laminate system through this transformation matrix. So in essence, I get the same formula as I got before, but instead of C here, I get S there. And this is actually the more convenient because I know S in the laminar coordinate system in a much easier way. And these don't have to be memorized. These are basically based on principal superposition, where you're looking at the effects of loading in one direction and seeing what happens in the other 2 orientations. And then the column vector and the diagonal terms here at the bottom 3 are related to the shear stresses. So again, I know S, which is on the right-hand side. I know T fully. That's a transformation matrix. And then I can find X, Y, Z. And I will find an expression like this. It will be probably fully populated. But the important thing is that given the ply angle, I can find T. And if I know T and I know S because I know the lamina properties, then I can find S in the laminate system. And these will be all numbers, okay? Some of them 0. So once I have this term, I can compare that to the laminate engineering constants. And you will find that when I find this number and this number and this number, that I can relate that to 1 over exx. I can relate that to minus nu yx divided by eyy, and so forth. So after I find this, I can relate this straight to the compliance matrix in the laminate system, and I'm able to then find effective properties, the effective Young modulus in the x direction, and the effective Poisson ratios, all in the laminate coherent system. You'll find these extra terms that were not defined earlier. We call those the shear coupling terms. And so they are almost like Poisson ratios, where if I apply stress in one direction, it causes shear in the other directions. So with that said, in summary, what we've accomplished is the following. Given the properties E11, E22, E33, and so forth in the laminar material orientations, we're able to find laminate engineering constants by transforming a single lamina to the X, Y, and Z coordinate systems. And the way we accomplish that is to derive the stress relationship for transformation from the lamina to the laminate system. We did it for the strain. And then instead of working with C, which is a compliance matrix, we worked with the stiffness matrix. We worked with the compliance matrix instead, because this one doesn't need memorization and is easier to work with. So now I have the laminate strain, the laminate stress. I can go through these transformations to find that given T, the ply angle, and I can find T fully, which is a 6 by 6. I know S in the laminar orientation. I can make this multiplication happen. And once I do that, I can then find X, Y, and Z. I will find this whole compliance matrix and will be fully populated. I'll compare that. I'll compare this to a matrix that should look like this. And then this will be 1 over EXX. EXX is the modulus in the X direction of the laminate coordinate system. And I will have known these values. I can compare this against that and find EXX very readily. Once I have that, I can look at the second term and find nu XY. I can then find a third one as nu XZ, and so forth. And then you can find all the different engineering constants that came about from rotating the ply angle to the laminate coordinate system. And as a consequence, you have additional terms that act like almost like Poisson ratios, but in a different way, where I apply loading in one direction and it causes shear in the other direction. So if we were to actually do the derivation for single ply at a ply angle alpha, you can show that the engineering constants in the laminate coordinate system will look like this, where M is the cosine of alpha, N is the sine of alpha. So given E11, E22, nu12, nu21, you can find EXX, and you can then do the same calculation for all the terms here. These ones are the nu XS that showed here, this term right there. I invite you to pause the video and take 20 minutes and kind of derive these equations so you can see that it will work out very readily. Congratulations if you're able to be the king of the road by being able to derive these equations. I highly encourage you to do that to get a fundamental understanding of how these equations came about. So we can plot the transform engineering constants and trying to understand what is going on. So here I've plotted EX over E2. So EX is the laminate coordinate system to is through the thickness, fiber direction, transverse to the fiber direction. And you can see here that if E to 2, if this angle theta was 0 degrees, or it was 90 degrees, you will find that EXX divided by E to 2 will become 1, which makes total sense because now EXX, E to 2 is aligned with the one direction, okay? You can also see the effects of ply angles on the transform system for GXY and G12. And you can see here, it changes quite a bit. You can see the effects of the Poisson ratio by transforming these angles. And I want you to notice what is going on here. So here, if the one orientation goes all the way to the y-axis, the 2 is aligned with the x, which makes sense why you get 1 when you have a theta of 90 degrees. You can also do a plot of EXX over E11 for plane weave, and you expect 1 and 1 at 0 and 90. That makes total sense. You also find that GXY equals G12 at theta equals 0 and 90. And then you can see the effects for the Poisson ratio. So I will now discuss how to find the effective engineering constants for multiple lamina. And what do we want to accomplish? We want to find, given multiple plies, what I want to achieve is to take these multiple plies and find the effective properties for a laminate. I did it for single lamina earlier, but what I really want to do is to find this for their whole stack, for multiple plies put together. And that's slightly a little bit of a harder problem here. So the theory to convert or to transform multiple plies and get the effective properties for the whole stack, not just a single lamina like we had discussed earlier, but for the whole stack, um, is based on a formula that was derived in the 1970s, 1990s, and it's one of the best theories. It compares well with test data. It does well with against multiple theories. And the current formulation is based on C.T. Sun's work, three-dimensional effective elastic constants for thick laminates. You can download the paper, but I'll also be discussing this topic today. There's a whole thesis by this gentleman that goes through that. We will try to go through that in this lecture. And what this does, this theory, I'll call it the Chow theory does, it allows us to basically specify material properties at the ply level. And then given the stacking sequence, you can find the laminate effective properties. What is the benefit there? Number one, I can get effective properties without testing, which you should test later on, but if you want to get properties ahead of time, this theory works very well. Number two, it can simplify greatly the finite element modeling of, say, a very, very large model, which could have a lot of material properties. But this could allow you to simplify it further by doing that. So there's two assumptions, two primary assumptions in Chow's theories. The first assumption is that we're going to assume that through thickness stresses for every ply, K1 through N, so K here represents the kth ply. So through thickness stresses are going to be equal and uniform for the whole plate. Again, the shear stresses, the transverse shear stresses for the kth layer are going to be equal to the homogenized stress in the laminate coordinate system. So this is one of the assumptions that is made in this theory. Uh, the second theory is on the basis of continuity of displacements at the layer interfaces. So we're going to assume that the in-plane strains are uniform and equal to the homogenized laminate. So what we're saying here, the in-plane strains in the laminate coordinate system for plies 1 through n are going to be equal to a single strain for the whole homogenized plate. So two very fundamental assumptions in charge theory. One, that the through thickness stresses in every ply is equal to a single stress set that represents the whole laminate stack. And second, that the in-plane strain from lamina to lamina does not change and is equal to the strain for the whole stack. In-plane strains. So those are the first two assumptions that we're going to make. The next two assumptions we're going to make is that the in-plane stresses are assumed, so the in-plane homogenized stresses are assumed to be an average stress through the thickness. So if I know the stresses at every ply, and I know the thickness of each layer divided by laminate total thickness, that the stress, the laminate coordinate system homogenized stress can be written in this manner. And so what we're really saying is that the homogenized stress for the whole system is an average of the stresses in plane from ply to ply. And then again, we again make the assumption that for the through the thickness strains now, that this is an average of the strains from ply to ply. So again, four assumptions here. For the through the thickness stresses, we assume that every ply has the same through the thickness stress, that for every ply, the in-plane strains is equal to a single homogenized strain set. And then for the homogenized stresses, that's the average of all the stresses in the in-plane direction. And then the strain through the thickness is equal to the average strain from ply to ply. So again, all we're trying to do here is to come up with an approach of finding equivalent engineering constants for a whole laminate stack that's composed of multiple plies at different orientations, whose properties are known in the material principal directions. And note here that K represents the ply, the ply number, and there could be n plies, and H is the thickness of each of those plies, and T is the total thickness of the stack. Because the weighted average is what these formulas are trying to accomplish here. So we already know how to deal with the kth lamina. So I know how to transform the stress, basically how to transform the lamina ply orientations to the laminate coordinate system using this formula. C is given here to the right, and T is known from here to the right. So given these two things, I know now how to transform the constitutive law for single ply. This is only for single ply, and I know how to do that using this formula here. So if C is known in the ply orientation, principal orientation, and I know T, the ply angle, then I can calculate C, the constitutive law, but in the laminate orientation for every ply. And that's what the K is here for. I can do this for every single ply, and I'll do that for every single ply. So if I have n plies, I have to calculate this n times. And what I'm going to do a little trick here. And the reason I'm going to do this trick is to be able to segregate the in-plane orientations from the out-of-plane orientations. And the reason I do that is because in Chow's theory, the stresses are put together, for the transverse shear stresses are put together, and the in-plane strains are put together. And you can see here that the stresses are in-plane and the strains are out-of-plane. So for that reason, we're going to apply a permutation symbol here, P. And the goal of that is by applying a permutation symbol P, which looks like this, this will automatically change the rows in such a manner that it will put them, it will segregate them. So how do I do that? I'll post-multiply by P inverse times P. This is an identity matrix, so that's not a problem. I will have pre-multiplied by P, so in this manner. And if I use P with this formula, and I multiply this matrix by this column vector, sigma z will switch to the bottom. And then sigma xy will switch to the third row. So that's just a trick. And also the strain here on the right-hand side, P times this vector, will allow us to segregate it in this manner. So it will have the out-of-plane strains in the bottom three, the in-plane strains of the top three, the stresses in the top three, and the out-of-plane stresses in the bottom three. So it's just a trick to basically get things organized. So I can apply Chow's theory. The next step here, what I plan to do now, we plan to take the top three and call that the in-plane stresses. And that's what we're going to call the sigma bold I. And the bottom three quantities will be put into the sigma s, which are the through thickness stresses. We also have the strains here, the top three. I'll call it in-plane strains. So this strain bold here contains three quantities. And then have a strain vector of out-of-plane stresses, which are the bottom three. So by doing this permutation symbol now, I know C now in the laminate orientation for ply K, and the P is known. That's just a permutation symbol. So this multiplication here is really here, is this one here, okay? I want you to note that this multiplication here is a 6 by 6. So we've segregated, we can segregate this matrix multiplication into four submatrices. This submatrix here will be 3 by 3, this will be 3 by 3, this will be 3 by 3, and this will be 3 by 3. So in total, you have a 6 by 6. And so that's what that really is. It's been segregated for the purposes of applying Chow's theory in a much easier way. Because as you saw, there's 4 fundamental assumptions made. And the fundamental assumptions made were that the through thickness stresses for every ply is going to be the same for the whole stack. That the strains for every ply are going to be the same for the whole stack, and then that the stresses, the homogenized stresses, are going to be the weighted average of the stress at every ply. And then we did that the same for the strains through the thickness as well. So what I've done here, I've been able to now put things in a way that I can apply Chow's theory. Here again is an exploded view, so it's clear what we've done. This matrix is fully known. Just keep that in mind. This one is fully known because I know C per single ply. I know the ply angles, I know the transformation matrix. So I know C at the laminate orientation. So I know this fully. So this C is fully known. The permutation symbol is known, but that was done on purpose so I can switch rows in a convenient way so I can organize and segregate it. between the in plane and through the thickness directions. So this is fully known. The H is fully known. This is fully known. And then here is your column vector, which has been segregated for the purposes of applying Chow's theory. So now, what I really want to do is I want to take the overall strategy to take this here on the left-hand side, which is on applied basis, and I want to convert that into a homogenized version of it. And I want to take the stiffness matrix, which is known by apply, single apply, and I want to get a full stiffness matrix for the whole thing, homogenized. How do I achieve that? Is a step-by-step process, okay? And so we have to like really go step by step to go through it. So we made these 4 assumptions in Chow's theory. I want to apply these 4 assumptions to the left, to this equation here, and do it in a way that I can bring it to the one on the right. That is the goal, is to somehow convert the stuff on the left, which is an applied basis, to the one on the right, which is the whole stack, looking at the whole stack, homogenized. And on here, the 4 assumptions. The in-plane stresses are the weighted average of the stresses in plane, ply by ply. The thickness strains are also a weighted average of the strains for every ply. And then the 2 main assumptions here are that the in-plane strains are the same for every ply, and the through thickness stress is the same for every ply. So 4 fundamental assumptions in Chow's theory. And this is what we had before at the ply angle level, at the ply level. And so what I'll do is I'll multiply this row by this vector. So I have this row by this vector. So I have this, and know that H is fully known. We know this fully, okay? And what I realize here is that EI superscript K is quickly EI superbar. I know that because this is the in-plane. We already said that the in-plane strains are the same for every ply, and they're homogenized in this manner. So I know that EI superscript K is already homogenized at EI over bar. I also know that for the second equation. We also notice that sigma S K, these through thickness stresses, is the same for every ply and is homogenized in this manner. So I can quickly convert sigma sk, the bottom 3 here, into sigma s over bar. So I have these 2 equations now. And so what I want to do now is somehow remove these k's, the ones on sigma and epsilon. I want to make them over bar somehow. And if I'm able to do that, I can then get closer to this here. So now that I have this equation, these 2 equations, I'm going to start working through that. I want to take the first equation here, sigma 1k, and then this one that's fully known, times epsilon I bar, plus HIS superscript k times epsilon sk. I want to take the first equation and walk through that. Okay, so let me go back one more time. Okay, so I have the second equation as well that can be transcribed. So I have this equation here. I can solve this equation. I can solve this equation for epsilon sk by inverting HSSK, pre-multiplying by HSSK here. I'm able to solve for epsilon s, which is through the thickness strains, like this. And then I can plug this in to here, to this one here. Okay, so first solve from the second equation, solve for epsilon sk, and plug that in the top equation. That's really what we did here. Okay, once I got to this, I can now substitute 1 into 2 to get that, basically. So solve for epsilon sk, plug that into the second equation. And this is what we get here. Okay, now things are getting messy, but don't lose sight that these H matrices are fully known. These are 3 by 3 3 by 3, 3 by 3. So these are all just multiplications, and there's nothing to be worried about at this point in time. But now what I'll do is rearrange, because I have epsilon I bar here and epsilon I bar here. So you can rearrange, and so you have this like that. Okay, so these two terms combine into that, this term combines into that. And so now I'll apply the summation symbol in the front and multiply by HK, the thickness of every ply divided by total thickness, in this manner. I can do that. And I realize quickly when I do apply that summation that this is really sigma I bar. But I have to apply that summation, this multiplication, to every single one of these coefficients. And that's why I get this little bit messy looking thing. But notice how I'm able now to get everything in terms of bars now, which was my goal. And these are fully known. These coefficients are fully known. This coefficient is fully known. Okay. And these are 3 by 3s. This whole thing is 3 by 3. This 3 by 3. So so note how we were able to get there so far. Things continue to be complex. We want to continue solving, so we're not there yet. This equation here is, I'm going to transcribe again. Okay. We solve for epsilon sk, so solve for that one. And now on this equation, I'll apply the average strain right away. So notice that I can apply the, we had made this assumption basically. This is epsilon s bar over bar for through the thickness strain. And we say that there will be the weighted average of the strains for every ply in this manner. So I know this formulation. So apply that summation to this equation here. And quickly I get that this epsilon s bar, and I have to apply the summation and multiplication to each of these coefficients. And I can now solve this equation right here. I can solve it for sigma s. Okay. And how do I do that? I have to invert this matrix or pre-multiply it by this so that I get these messy terms. Okay. But notice how sigma s bar is in terms of epsilon s bar and epsilon I bar. So I was able to remove this case here, epsilon sk, which was my goal. Okay. So now I have this one at the bottom, and I have this one at the bottom. So two equations so far. So I can continue solving. So this sigma s bar can now be plugged in into the previous equation. I can plug it in here. And when I do that, I can plug it in here. When I do that, now I can put it in this form. I can put it in that form, which is what I want in the first place. And it's messy, but you can get there. So each of these terms are defined here at the bottom. AII bar is this one, over bar, AIS is this one, and so forth. The important thing is I'm able to find this A matrix, which is fully populated, is a 6 by 6, and represents the compliance matrix for the laminate coordinate system. And the good news is that once I have this, what I want to do now, I want to use a permutation symbol, but in reverse. I want to bring back everything. I want to bring back everything to what it was. I want to bring the sigma z back where it should go, epsilon z back where it should go, and you can do that by multiplying by p in this manner. Okay. So I know it is a bar. I know this a bar, pre-multiply by p, post-multiply by p inverse, and I will get the C matrix in the laminate coordinate system. So here we are. Once you know C bar, you can invert that to get S bar, over bar. So basically invert this equation to get this one. Once you know S bar, which is fully known, the left-hand side is fully known. Since you know the left-hand side, you can now solve for EXX bar, nu XY bar, and all these different material constants. So you will get 13 material constants, including shear coupling terms. But the important thing is that we were able to come up with a way. And so let me revisit again what we've done really quickly. Given the ply properties in the 1, 2, and 3 direction, we were able to use an approach that allows us, given the stacking sequence, come up with the equivalent effective material properties in the X, Y, and Z directions. And that's very powerful on how we've done this. We used the Chow's theory, 4 assumptions, came up with a way to do so. So once I have these coefficients, what I've done is really found the properties without having to do any testing, which can be verified to do very well against testing as well. So this can also be used to kind of do some spot check to your test, make sure that everything is in good shape from the testing perspective as well. But the two fundamental benefits is you can simplify the finite element modeling, and you can get properties in advance of any testing. So I invite you to take some time for extra credit. If you can implement a code that can perform these calculations, given the basic engineering constants for each material, the ply layout, the thickness, the material for each laminate, we would like to calculate the effective engineering constants for the laminate. And then I will provide some examples to see if your answers are on target. I hope that this lecture was clear to you. I invite you to kind of derive all the equations listed in this briefing, and that it's clear to you, and the motivations behind these are very clear to you. Thank you very much for listening, and have a great rest of your day.